We are going to talk a little bit. I have one more thing to say about conditional versus absolute convergence, and then we can just go on and talk about our next test. Next convergence test. Speaking of test, our usual, I said this last time, but I'll say again, our usual quiz, which was going to be on Friday, is not happening on Friday, so we'll just do it on Tuesday. So the quiz will cover what's on the homework for today, which is the integral test and the comparison test. So all of that will be on Tuesday. All right, let's talk about, I will just refresh your memory about absolute versus conditional convergence. Absolute versus conditional convergence. Absolute meaning, the word absolute refers to like the absolute value. So for some series a to the n, some series an, the sum of an, if the absolute value of an, that series converges, we say that the original one, without the absolute values, is absolutely convergent. All right? Absolutely convergent means it converges even if you put absolute values around it. All right? And at the end last time we showed that absolutely convergent actually implies that it is convergent. So anything which is absolutely convergent automatically is convergent in the ordinary sense, but absolutely means it not only the thing converges, but also the thing converges when you put absolute values around it, which, if anything, putting absolute values around it makes everything bigger, because anything that used to be negative is now going to be positive. So it's kind of harder for this one to converge because everything is bigger. And so it's, I would say, more likely that this one goes to infinity. Even if you know this one converges, it doesn't necessarily mean that this one converges. So if this one does converge, though, it's called absolutely convergent. And then if that one doesn't converge, but the other one does, so then it's called conditionally convergent. So that is if this one converges, but the absolute one does not converge, the absolute one diverges, then this sum of an is called conditionally convergent. Conditionally convergent. That means it does converge, but only when you keep the signs the way they are, not if you put absolute values. Putting the absolute values causes it to diverge. That's called conditionally convergent. All right? And I have one very curious fact about conditionally convergent series, which I think is very interesting, and I can even remember as a young lad when I first learned this fact about conditionally convergent series. It had quite an effect on me, I guess. I don't know. I still remember. This, in my opinion, is a very strange but true fact and somewhat inspiring. I don't know. Something that I like about mathematics is that it's full of strange but true facts. Most of math, especially like when you're a kid, everything just kind of makes sense. And there's not a lot that's really like surprising about, learning to add fractions or something. This is in my opinion. But there are actually in higher level math, there are things that are like genuinely surprising. Anyway, the typical example that we talked about last time of a conditionally convergent is this. This is called the alternating harmonic series. If we alternate the signs, minus a sixth, all the even ones are negative and all the other ones are positive. This is called the alternating harmonic series. And it is conditionally convergent. We showed this last time, that this one, as is when you add them up, it converges. But if you take the absolute values, you get the ordinary harmonic series, which diverges. So it is conditionally convergent. And in fact, we haven't talked about this, but we are eventually going to talk about a method by which you can actually add it up and see what it converges to. So I'll just say, we'll get to this next week. Maybe I mean, certainly before the end. We only have really 2 weeks left after today. But anyway, turns out it does converge. This thing plus a third minus a fourth plus etc. This actually converges. This is very weird, but it adds up to the natural log of 2. We're going to talk about why that is true later on. But for now, would you just believe me? This is something like 0.6931. I put this into my calculator. This is not the surprising fact, although that fact by itself is also surprising. Remember what it means when I say this converges. It means that the partial sums eventually get very close to this. So in fact, I did this on my calculator. Actually, I did this in Excel because this is a nightmare to do on my calculator. We can calculate the 100th partial sum. That would be just adding up all the first 100 of these. And because I said this converges to that number, you should expect the 100th partial sum to be pretty close to that number, because that's what this number represents. It means if you take a whole lot of these together, they will eventually get really close to this. When I did this in my Excel, I got 0.688 something something, all right? Which is, I mean, getting pretty close to the value that I expect it to converge to, 0.69, all right? That's the 100th partial sum. I would like to point out, in this example, the 100th partial sum would represent taking, in terms of like the positive ones and the negative ones, it would represent taking like 50 of the positive ones and 50 of the negative ones, right, at the beginning. Obviously, if you take the first 100 of these, half of them, you're getting the first 50 positives and the first 50 negatives. I only mention this because it's going to be interesting and it's something weird I'm about to say. But this is the first 50 positive terms and the first 50 negative terms, right? Okay, that's what the 100th partial sum. If you take more partial sums, like S sub 1,000, that would be the 1,000th partial sum. It would add up to even closer to that number that it's converging to. All right, great. Here is the strange thing that I would like to draw to your attention. What if we add them in a different order? All right. Perhaps you've heard of something called the commutative property of addition. It means that it doesn't matter what order you add numbers in, right? Like 1 plus 5 is the same as 5 plus 1. This is a basic fact that even little kids understand this. Like, as soon as you learn how to add, your teacher tells you this fact. I have a friend who's a preschool teacher. Even she tells her kids about this fact. She has a cute name for it. It's called like the switch fact or something. If you switch the numbers around, you get the same answer when you're adding, right? Not true when you're subtracting, of course. But anyway, what if we add these numbers up in a different order? Let's take, so these guys here, let's take, instead of alternating one of the positives and then one of the negatives and then a positive then a negative, let's take like 2 positives and then a negative, and then 2 positives and then a negative. I'm using the same numbers though, so let's do what I mean by this: 2 positives and then a negatives. 1 and a third, those are the first 2 positives, and then a negative, minus a half, and then 2 positives, 1/5, 1/7, and then a negative, etc. All right? These are all the same numbers with the same signs. All I did was rearrange them, all right? I'm not introducing any new numbers or changing the signs of any numbers in the list. I'm just writing them in a different order. So this is 2 positive for each negative, right? 2 positives and a negative, then 2 positives, then a negative. But this listing, this is weird, but this listing still does include all of the positives and all of the negatives. They eventually do appear in this list. So it is the same numbers appearing in the list with the same signs. But what happens if we add these up now? What about the partial sums here? So here, what is S100 this time when I rearrange them? Well, okay, before this S100, which added up to 0.688, whatever, this represented the first 50 positives and the first 50 negatives. That's just because they were alternating in this version, all right? But in this version, when I add these up, actually if you take the first 100 of them, most of them will be positive this time because I'm taking 2 positives for every negative. In fact, you can say like 2/3 of them will be positive and only 1/3 of them will be negative. So in this case, S100, this would involve something like the first, it's not the first 50 and 50 positive and 50 negatives. Actually, it's like 2/3 of them are positive. It's something like the first 67 positives and the first 33 negatives, right? This time the partial sum has more positives than negatives. And specifically it has 2/3 more. And so what is this S100? Actually, it is not the same as this number, right? This number represents the first 50 positives and the first 50 negatives. This one represents these, and it's different. And actually, I did this on my Excel also. I got 1.039, all right? It turns out when you do these partial sums for this one, they are always going to be greater than these partial sums for this one. It's because this one involves sort of front-loading the positives, and so anytime I try to add up some of them, I'll be sort of like biased towards the positives in a way that was not the case up here. In this case, I'm kind of even positives and negatives, all right? So what I'm telling you here is this one, which I rearranged, these partial sums, no matter how far down the list you go, these are always greater than before after I rearrange them, all right? They're always greater than before because I'm taking more positives at the beginning than negatives. And what that means is, so the series, it does not converge to the same number. That's what I'm telling you. The series converges to a different number, not the same number from before, all right? So what I'm telling you here is, here's the, you can tell your moms during the break, this thing here and this other one, when I just use the same numbers but in a different order, these two things, they add up to different numbers. This is the strange and surprising fact. I hope that this seems strange and surprising to you. It means what you learned as a little kid about rearranging the order of additions, when you change the order, it doesn't matter what it adds up to. That is only true for adding finitely many things together. But if you add infinitely many things as a series, actually the order can matter. And in this case, the ordering, changing the order makes them add up to different numbers. All right. This is a strange and true fact. This is only possible by playing games with the signs, the positives and the negatives. If you start with a series where they're all positive, actually you can't do the same trick. This only works in this example because some of them are positive and some of them are negative. In fact, this only works, but it does work for any example. This works for any conditionally convergent series. And this is has sort of a name for this fact. You can tell when you're telling your parents over the break about this fact. We learned this is called Riemann's rearrangement theorem. Riemann is one of the great kind of figures in the development of calculus. Riemann's rearrangement theorem. Riemann realized this fact. It says if series AN, if this is conditionally convergent, then rearrangements of the series may converge to different values. It's true. If you write the same exact numbers, but just in a different order, you can make it add up to different answers. And it's even better than this. This, I think, is really very cute. In fact, actually, to say it even better, for any real number L, there is some rearrangement which makes it add up to L. This is true of any conditionally convergent series. There is some rearrangement, or I'll say that. For any real number L, there is some rearrangement which makes it add up to L. What that means is no matter what number you want it to add up to, you can actually make it add up to that number by rearranging the terms in some way. So for example, what this means is like this one, the alternating harmonic, like I said before, this actually, in that order, it adds up to the natural log of 2, all right? But what if I wanted instead for it to add up to 0? Is that possible? What the theorem says, and this is what I just said here, for any real number L, there is some rearrangement which makes it add up to L. So that means, now it's not very easy to say what exactly the rearrangement is, but so this adds up to natural log of 2, but we can reorder it so that it converges to 0 if you want, all right? The theorem says for any number, you can always rearrange it so that it adds up to that number. So you can reorder it if you want to so that it converges to 0, or you could rearrange it so that it converges to pi, or any number you can think of, or you could rearrange it so that it converges to my favorite whole number, 8675309. Remember that one? It is possible to rearrange this sequence. In order to make the answer, this is a very sort of large number. You would have to front load a lot of positives here to make it add up to a number this big. But it is possible to do that. That's what Riemann's rearrangement theorem says. This is not just a fact of this particular example, but it's true of any conditionally convergent sequence. Very strange and interesting, in my opinion. Anybody got any thoughts about this? It means that this, the commutative property of addition, it is true if you're just adding 2 numbers together or 3 numbers together, but it's not necessarily true if you're adding infinitely many things together in a series. All right, great. Fun fact about the nature of numbers. All right. This is all I wanted to say about absolute and conditional convergence. If you ask me, this is the most interesting fact about conditional convergence. It's the only fact that I care about conditional convergence. To me, this is super surprising and very interesting. Let's talk about something else then. That was just a last leftover bit of something about conditional versus absolute convergence. If the series converges absolutely, you can't do any of this funny business. So if it converges absolutely, then all reorderings will have the same sum, and there's no opportunity to make it add up to different numbers by reordering. But if it's conditionally convergent, then you can reorder it to add up to whatever you want. All right. So when I said before, like this actually adds up to ln2, and that's an interesting fact all by itself. But I mean, it's only in that ordering that it adds up to ln2. If you wanted it to add up to ln3 instead, actually there is a way to reorder it so that it adds to ln3 or whatever you want. Strange. All right. Anyway, let's talk about something a little more down to earth. The next of our convergence tests, and I believe this is going to be the last of our tests, and then we'll talk about there's sort of one last big topic before the end. This is called the ratio test. I actually really like the ratio test. In a lot of ways, it's easier to do than our other tests. The ratio test. So I would like to refresh our memory a little bit. So I just want to tell you sort of where the ratio test comes from. So remember, one of our standard remember, yeah, the geometric series. This is one of our standard types of series that we talk about all the time. The geometric series is one in which the ratio of one term to the next, this is the one with the A and the R, right? In general, they look like this. But where the A is the first term, and the R here, the R is what we call the common ratio. The common ratio. So if my sequence is something like, here's a very simple one, 1 plus 2 plus 4 plus 8 plus 16. Here the R is 2 because the ratio, every number divided by the previous one, is always 2, all right? Everybody knows this. Here the R equals 2, since in this case, an plus 1 divided by an equals 2 every time, right? That's what makes it a geometric series. A geometric series is one in which that ratio is always the same every time. And in this example, that ratio equals 2. And because of what that ratio is, we can tell if it converges or not. And the rule everybody knows, if R is more than 1, it diverges. Actually, if R is greater or equal to 1, it diverges. And if R is less than 1, then it converges, right? So this equals 2 every time, and I will just say this diverges since R is greater than 1, right? Now, I would like to talk about something like this, but not for something which is exactly geometric in this way. So what I would like to discuss is, what if the R is not the same every time, but it's like a little bit different every time, but still kind of the same? So this I'm going to say in more formal language in a moment. But what if the R isn't quite the same every time? All right, can you still say anything about converging when the R isn't quite the same every time? What that means is, i.e., an plus 1 divided by an is not always the same number, but it's just like you get a different answer every time, all right? Now, if those answers are just totally different every time, you really can't say anything. But if those answers are all kind of close to one another, and in particular, let's assume that if this has a limit, and I'll call it L, although you should think of L as being, kind of like R, right? We call it R when they are actually literally the same every time. But here, I am assuming that they're not necessarily all the same every time, but at least when you look far down the list, they approach the same value every time, all right? That's the idea. So L is like R, although it's a little looser. They don't actually have to be the same every time. They just approach something, all right? But anyway, if it turns out when you do this ratio, if they approach something, then it turns out the convergence is the same using L in place of R. What I mean is, if the L is greater than 1, it diverges. And if the L is less than 1, it converges. So if that limit exists and I call it L, then the convergence is the same using L in place of R. So I'm going to write this more formally. That's the basic idea, though. These sequences doesn't necessarily have a specific R every time, but those ratios are approaching something. And this is called the ratio test. So I'm going to write this formally here. The ratio test. This is about a situation when you don't quite have the same R every time, but you still have something that converges somewhere. The great thing about the ratio test is it works for any series. Our other tests all had some kind of caveats, like it always has to be positive, or it has to be decreasing, or whatever. Not so for the ratio test. For any series, the sum a to the n, I'm going to write this in 3 parts, although this is very easy to remember. So the first part says if the lim, can I write it? Sorry, I want to write it a little bit differently. Sorry. I know that's annoying when I do that. For any series, I'm going to say let L equal the lim n goes to infinity of an plus 1 over an. All right? That's the value that takes the place of R. And then the rules about convergence, it says, then I'll just write this in 3 parts. If L is greater than 1, then the sum an diverges. All right? And this case actually includes the case when L equals infinity. That happens sometimes when you take this limit. Sometimes you get positive infinity, but that still counts for the purposes of the ratio test. That still counts as being greater than 1. So this, I will just say parenthetically here. Even when you take that limit, if you get infinity, that still counts as greater than 1. Ordinarily, I feel uncomfortable saying infinity is greater than 1 just because infinity is not really a number. But this case also applies when L is infinity. Okay, case number 2. If L is less than 1, then the series converges. In fact, it's even better than that. Then this is absolutely convergent. Although usually all you care about is that it is convergent, which is also true. But this is even more so. It turns out to be absolutely convergent. You know what? I'm sorry, I left out. This is easy to add in. There have to be absolute values around this L here. I left them out before, but there should be absolute values here. All right, that makes it so that you're not going to get negative answers for L, which muddies the waters a little bit if you allow negative answers. I'm only talking about absolute values. Okay, and then number 3, if the L equals 1, I didn't actually discuss that, and this is kind of the bad news about the ratio test. It's inconclusive. So in that case, you just can't use the ratio test and you have to use one of our other methods. So if the L turns out to equal 1, it's inconclusive, and I'll just say you must use another method. You know, use the integral test or the comparison test or something else. All right. But this is the ratio test. It looks kind of like the limit comparison test, which also involves a ratio, but it's really a different thing. This is not comparing a ratio of one sequence with another sequence. It's just the sequence with itself. You take that limit, and then based on if the L is more or less than 1, you can say if it converges or not. All right. This is called the ratio test, and it's quite useful, especially because it works on any series, not just one where it's positive or something like that. Our other ones all had various conditions that needed to be true in order to use them at all. All right, let's try some. I got 2 here, and then I got 1 for you to try, and that'll probably do it for us. Using the ratio test, let's. Another nice thing about it is it does tell you if it converges or it diverges, right? The one we talked about last time, the alternating series test, could only tell you if it converges. It could not tell you if it diverges. All right, how about this one? Does it converge or not? That's the question. Does it converge? I'm going to use the ratio test, surprising no one. So here, my an is n over 2 to the n, and you have to make this lim, n goes to infinity, absolute value of an plus 1 over an, right? That's my L. And if you can plug everything in properly and do the limit, whether, depending on the answer you get, if it's more than 1, it diverges. If it's less than 1, it converges. And that's all there is to it. So all you got to do is plug in properly and take the limit properly. So let's plug in. I have an plus 1 on the top. Of course, we have to consider the absolute values, which will sometimes be a pain to deal with. But an plus 1 on the top is n plus 1 over 2 to the n plus 1. I am plugging in n plus 1 instead of n everywhere you see it in the sequence here. That's an plus 1, and then dividing by an. An is just n over 2 to the n, right? I put an extra long fraction bar there. Okay, as usual, this division of fractions I'm going to write as multiplying reciprocals, just because that is less confusing to me. So it's the top, as is, times the reciprocal of the bottom, like so. And now we cancel as much as we can here. I forgot the absolute value signs. Eventually, when you're doing these problems, you can hope to just throw away the absolute value signs. Do we really need the absolute value signs? In this example, I would say these absolute value signs don't actually do anything because everything on the inside is already positive, right? N is positive. I don't see anything inside which could ever be negative. And so this is positive, so I don't, in the next step, I'm just going to get rid of the absolute value signs. But anyway, what else can cancel here? These n's, I find it helpful to sort of collect things, similar things together. I'll put these n's here and then these 2's here, right? I just rearranged the numerators and denominators a little bit to put things together where they go together. And then the 2's business, I can cancel things here. What does this simplify to? Any thoughts? Yeah? 2 to the minus 1. Yeah, you are sort of subtracting exponents here. Or you could say I have n 2's up here and 1 extra down here, so when I cancel them, there's going to be like 1 left over at the end. I will write that as n plus 1 over n, and then times a half, right? He said 2 to the minus 1, which is the same thing. All right. And then can we do this limit? How would you take this limit? I don't think you can simplify it anymore, but we should try and do the limit now. What do you think? Yeah? Yeah, divide everything by the highest power of n. That's what I would do. So here, the highest power of n is just n. Divide everything through by n. This 1/2 can just stay like it is, I guess. This will say 1 plus 1 over n over 1, right? And then taking the limit makes that little 1 over n turn into a 0. So I get 1 plus 0 over 1 times a half. The answer is a half, right? Because that thing at the beginning turns into a 1. Okay, so L is a half. So L is less than 1, so it converges. Right? It's the same rule for the R's. If the R is less than 1, it converges. If the R is more than 1, it diverges. Oh, in the case of the L, if the L equals 1, then you just can't say either way. But this one converges. Right? Let's try one more, and then I got one for you all. How about, this one looks crazy, but it'll be fine. Don't worry about it. How about that? All right. The minus 1 to the n means this is alternating, which you might think is gonna cause some headache for us. Actually, it doesn't matter almost at all. All right. But anyway, in this case, my an, I'm just going to do the same thing. So an in this time is minus 1 to the n, e to the n over n to the 8. You might also be worried about e to the n. Don't worry about it. It's going to be similar to the one that we just did. So I set up my L. It's the lim, absolute value, an plus 1 divided by an. This is lim, absolute value. Would you mind if I just immediately write this as multiplying the reciprocal? So I have an plus 1 first, written, not as the reciprocal, the normal way around. This is an plus 1. I don't like the looks of n plus 1, the whole thing to the power 8, but I guess we'll deal with that eventually. This is an plus 1. And then times the reciprocal of an. So now I'm going to multiply the reciprocal of this formula here. That's n to the 8 over minus 1 to the n, e to the n. Right? That's the reciprocal of an. And now we got to simplify things. Like I did before, I'm going to try and gather together the various parts that look the same. Keep them in numerators and denominators as appropriate, but the first, and we'll have to talk about the absolute value signs, but let's put the minus ones. I have minus 1 to the n plus 1 up top, minus 1 to the n on the bottom. And then how about the e's? E to the n plus 1 on top, e to the n on the bottom, and then the n's, n to the 8 over n plus 1 to the 8, like that. All right, and now, first of all, let's talk about the absolute values. Can anybody say what's the effect of the absolute values here? In the previous example, they had no effect at all, and I just threw them away. That's because nothing in here could ever be negative, and so the absolute values don't do anything. What about in this case? Yeah?
Does it get rid of the alternating signs?
Yeah, all the absolute value signs will do is kill this part. So this part could be negative. In fact, I think it definitely is negative. If you cancel n's here, you just get minus 1 to the 1. But anyway, that affects the sign. This business over here is all positive, though. So the effect of taking these absolute values is just to remove that, and then everything else stays like it is. So this is just the same as this. This part is always going to be positive. The other thing determines the sign, and when I take the absolute value, it means we can ignore the other thing. Just keep this business. All right, and then how do we simplify this? Well, e to the n plus 1 over e to the n, you can subtract exponents here. I think I end up with just e to the 1, just e. So this is lim e, just the number e. So we don't have to worry about that. That's just going to be a constant, right? And then the rest of it, n to the 8 over n plus 1 to the 8. This is a little weird. Like I said before, I don't like n plus 1, the whole thing to the 8. In theory, you could expand this, but this would be a nightmare to do. It's like do the FOIL 8 times here. I never want to do that. Here's a trick, though. Check it out. That is the same as this. This is a trick that you might often use when doing these problems. It is a fact that taking a power of a fraction is the same as that power on the top and also that power on the bottom. And now we can do this limit because the limit inside here is 1. That's just like this one, right? So I'm going to do that same old divide out the power trick, dividing out the largest power of n, which on the inside is just n to the 1. So leave the e, that's just a constant multiple. And then here I'm going to write this as 1 over 1 plus 1 over n, whole thing to the 8. All right, I divided out the biggest power of n, all inside of the exponent of 8. And now we can take this limit, leaving the exponent of 8 out there. It becomes e times 1 over 1 plus 0 to the 8, like that. That's the step where I did the limit. And then what is that business inside the parentheses? It's just 1, because it's 1 divided by 1. And 1 to the 8 is just 1, so the whole thing is just e. This thing here is all equal to 1. All right, so L is E. Anybody remember, is E more, greater or less than 1? That's what we care about at the very end, is L being greater or less than 1. What is E? Remember? Yeah, it's greater than 1. E is like 2.7 something, I think. I don't know. People don't memorize the digits of E like they do for pi. But anyway, so L is greater than 1, so it diverges. That's the rule about L. L less than 1, it converges. L greater than 1, it diverges. L equals 1, nobody knows. All right? This is the ratio test. I got one for you to try, and then I think that'll do it for us for today. Let's try the sum n 2 to the n over 5 to the n. See what you think. Does it converge or not? This is your job. Actually, can I make it a little more fun? Make it n squared up there instead of n. Can you handle that? It'll be great. How much of the one that we just did? All right, can we talk about these just because we got to go? I see lots of people making good progress here. You should start off by writing this. This is multiplying times the reciprocal. And then I'm going to group together the buddies, the buddy system. So put those guys together because they are buddies. And then the 2s I put together. And then I put the 5s together. All right? And then some of these guys can cancel exactly as is. First of all, maybe can I say the absolute value signs are not necessary in this case. Everything on the inside of there is always going to be positive, so we don't have to worry about the absolute values. Can I just erase them here? The absolute values have no effect. What about the various fractions? This is a trick just like we did in the previous example. I'm going to write the first one like that. And then the next one, 2 to the n plus 1 over 2 to the n, you can simplify that by subtracting exponents. N plus 1 minus n is just 1. So the next one is just 2 to the 1, right? And then the last one with the 5s, again, you can simplify this. Everything will cancel except there's an extra 5 on the bottom. So this is 1 over 5, or you could think of it as subtracting exponents and you get 5 to the minus 1. It's like that, all right? And then what happens to when I take the limit? You know, these guys just are going to stay there. This, in here, we have to deal with this n. And again, I'm going to do the divide by the biggest power of n trick, which is just 1, n to the 1 in this case. So it's going to be 1 plus 1 over n over 1 times 2 times a fifth. I'll write as 2/5. All right. And then taking this limit, the 1 over n becomes 0. So it's 1 plus 0 over 1 squared times 2/5. All of this business is just 1. 1 plus 0 is 1. 1 over 1 squared is 1. So the final value of L is 2/5. And therefore, 2/5 being less than 1, it converges. All right, that's how it's done. I hope you all have a nice little break. Like I said last time, I will be available right now for the next hour to talk about the homework. Unfortunately, I'm busy after that, but if you want, I would be happy to try and help by email or something like that. See you all next week for the quiz on Tuesday.